Testing, testing. 1, 2, 3, 4. I hope this is working. Okay, so what I'm doing here is I'm going to redo section 2.3 because there were a lot of questions on that. So I just want to make sure everybody's clear on it. Plus, Zoom recordings don't save as a particular name or date. I got to figure out if that can even be done. And it makes them really hard to find. But section 2.3 is the derivative function. So let me go back and state this very important bit of information. And it is this, is that on an interval, okay, some interval from A to B, the average velocity, which is the same as the average rate of change, is equal to the slope of a tangent line, which connects the endpoints of the interval. So if I have some function, call it f here, and I have some point A right here, and I have some point B right here, then I can connect those two endpoints of that particular interval with a, shoot, I said tangent line. Yikes. Secant line. So let me say it again. The average velocity or average rate of change of a function, okay, is equal to the slope of the secant line that connects the endpoints of the interval. So what we want to find, this is our secant line. It's just a line, and we want to find its slope, okay? The slope of that line is going to be equal to the average rate of change or average velocity, depending on the context that the problem is given in. And I'm sorry, I have to drink lots of ice water because my throat is not right. Okay. Now, so let me find another color here. This would be the point A, comma, f of A. And this would be the point B, comma, f of B. So we can also say that the slope of that secant line is equal to f of B minus f of A over B minus A, which is just the change in y over the change in x, which you learned in algebra as y sub 2 minus y sub 1 over x sub 2 minus x sub 1. Okay, it's all the same thing, just a different notation, right? Now remember that we also said that all of this stuff here, all of this stuff, all of these formulas are all equivalent. And so again, I'm going to say that the average velocity is equal to the average rate of change of a function over an interval from A to B, which is just simply the slope of the secant line of the connecting the endpoints of that interval that's given, okay, which is equal to f of B minus f of A over B minus A, which is delta y over delta x, which is y sub 2 minus y sub 1 over the change in x, x sub 2 minus x sub 1, which is also equal to the difference quotient, f of A plus h minus f of A all over h, okay? Now, the difference quotient comes into play because you got to remember that these points A and B here are really, really close together. So again, if I could replicate this graph, and I probably cannot, what I want you to think of is that, well, this is not going to be a good rendition, but if this is point A here, point B is like right next to it. This part here is just blown up so that they look far away. But the idea is that, you know, I can draw this little tiny secant line here in red in between them, okay, and get the slope. And that's really important because what this means is that if this is A, f of A, and I move over some teeny tiny bit called h, some teeny tiny difference, then this b becomes a plus h, okay? And this becomes a plus h comma f of a plus h. So I'm using the same formula for slope. It's just f of a plus h minus f of a over a plus h minus a, which gives you just an h on the bottom. So this too is just delta y over delta x. There is no difference except for notation. They all mean the slope of a line between the 2 points. Now, when you find the slope of the secant line or the average velocity or the average rate of change, what you're getting is a number, like 3 or 5 or something. Maybe 40, maybe 60. It's a number, okay? And what we learned is that, we're trying to hone in on some specific point, because eventually this led up to the notion of instantaneous velocity or instantaneous rate of change. Instantaneous rate of change or instantaneous velocity, we call it velocity, we call it instantaneous velocity, we call it instantaneous rate of change. We know that's the slope of the tangent line, okay, to some particular point. So it's no longer over an interval. So if I have some function here, f, and this is a, and this is b, okay, the idea is if I draw a tangent line to this point right here, then the idea is I'm trying to make the slope of my secant line using that difference quotient equal to the slope of my tangent line, so that way I can find the instantaneous rate of change. So remember, we moved over this really teeny tiny distance called h, which makes this point become a plus h, right? This point of tangency here is the point a comma f of a, and this point right here is the point a plus h comma f of a plus h. That doesn't change. The thing is if I draw the slope between this point and a plus h, so I draw this line here, this is a terrible picture because the slope of my secant line sort of coincides with the slope of my tangent line, which I didn't want. But the idea is that, maybe my tangent line is really more like this. Oops, wrong color. We'll call this the tangent line here at this point A, okay? The slope of my secant line is going to be a good approximation of my tangent line, but it's going to be pretty inaccurate because the slopes look nothing the same. The red tangent line looks much steeper. This is much steeper slope than this one. So there's going to be, there's going to be error there or inaccuracy. So the idea is that I'm going to take this and move it a little closer, right? So we had done that before. So if I move the point to say here, and I compute the slope of that secant line, well, they're still really way off at this point here, right? Again, my a plus h would just move, okay? Because what I'm doing is I'm reducing that width of my interval. And we keep moving this point closer and closer and closer until the slope of my secant line is equivalent to the slope of my tangent line. So we say that the instantaneous velocity or instantaneous rate of change is equal to the slope of a tangent line, which is equal to the limit as the width of the interval goes to 0 of f of a plus h minus f of a over h. So this is equal to the derivative of the function at the point where x is equal to a. So again, when you work that out, you're going to get a number, okay? So in both cases, you're getting some number. Now, where section 2.3 differs is, we're not looking for the derivative at a point anymore. We're looking for the derivative over the entire domain of the function. So every point from a to b, including a and b if we can. I'll tell you right now that derivatives don't exist at endpoints. Left and right-hand derivatives do, but generally what we're looking at is all points on the interior of the interval. Okay, and every function has a rate of change at every single point, except again, those endpoints are special. So forget about the endpoints for right now. So when I take the derivative of a function, I get a new function, all right? So the derivative of a function, you notice there's not an A in here anymore. I'm not talking about a point, I'm talking about all points, is equal to the limit as the width of the interval gets really small of f of x plus h minus f of x all over h. In other words, when I take the derivative of a function, I get a new function, which is called the derivative function. And that's what section 2.3 is all about. So let's go back there. All right, so initially, how this section is introduced, and it's introduced in a good way. George Best gives you this parabola, and this is just y equals to x squared. We know this function has its vertex at the origin, okay? And what he has here are these little tangent lines, little tangent lines drawn at different points along this curve, okay? To give you the idea of, we can graph the derivative function pretty accurately if we can do a lot of work and figure out what the slopes of each one of these are. Now this one's easy. We know the slope at 0 is 0 because it's flat. So that's an easy one to spot without doing any work. But for the rest of these, what you have to do is, you know, like for instance at x equals to 1. So let me erase. Okay, and let me show, let's see, when x is equal to 1. Well, if this is the function y equals to x squared, when x is 1, if I plug a 1 in for x, y is also 1. So those two make sense there, all right? They got that the slope of the tangent line was 2. Well, how did they do that? Well, we know that this is the point 1, 1. And what they did was they extended this tangent line out until it hit some nice, perfect little intersection in the grid. Let's use, what is this, 2, I can't see that, 2, 3. This is the point 2, 3. And you're going to compute that slope. So the slope is equal to 3 minus 1 over 2 minus 1, which is 2 over 1, or 2. So that's how George Best got the slope of 2. Now, it's just an approximation, but it's the best we could do. And we'd have to do that for every single point along the graph to get these numbers out, these tangent slopes, okay? And then what we would do is we would take the coordinates x, f prime, and plot them to get the graph of the derivative. So if I just superimpose over this graph here, again, using these two columns here, so let me highlight it. So I'm going to use this column here for the x values. I'm going to use this column here for the y prime or f prime values. Then if I go ahead and plot those, I'm going to have the point -2, -4, which is somewhere down here, okay? And then -1, -2, and then 0, 0, and then 1, 2, and 2, 4. So is 4 up here? I think so. And it makes sense because I told you that we drop a degree for every derivative that we take. It makes sense that I'd go from a quadratic function here, right, something x squared, to a linear function. Now, again, we can plot them like that, and it's a lot of work, so we just don't do that. Rather than that, we curve sketch. And by the way, here's the graph of the function above, and here's its derivative. You notice this is a function in terms of x, this is a function in terms of x. There's no number because we're not finding the rate of change at a particular point on this graph. We're finding it over every point on this graph. So the derivative of a function is a new function, and that function is called the derivative function. Okay? Here's another one where we're going to do the curve sketching. Now, this is where the gospel comes in, right? So remember, the gospel says that when the second derivative is positive, that means that the graph, so we're talking about the graphs now. When the graph, the second derivative is positive, that means that the graph of the first derivative must be increasing, which means that the graph of f must be concave up. When the graph of the second derivative is negative, that means f prime graph is decreasing and f is concave down. When f is increasing, we know that the derivative graph has to be positive, and when it's decreasing, we know that the graph of the derivative has to be negative, meaning negative below the x-axis, positive above the x-axis. So what I told you to do is when you're given the graph of f, and we're given one right here, first and foremost, you find the bumps on the graph of f, okay? I have a bump here, and if I draw a tangent line to that bump and a tangent line to the other bump, we see that the slopes of those tangent lines are 0. So what it means is that on the graph of f prime, or the derivative, those are going to be the zeros of the derivative. So we just project them down as the zeros on the graph of the derivative, and I will be graphing the derivative in red. Okay, now let's use the gospel. I don't know anything right now about the second derivative, so I'm not even going to consider that. What I do know is I can see where f is concave up. It's concave up from about right here to here. It's also concave down from about here to here. So I know some things about the second derivative, even though I can't see its graph. The other thing I know, though, is right here. So this is what we're going to stick to. What I know is that my function f is increasing from -4 to -1.5. So what I know is that my derivative graph has to be above the x-axis. Now I really don't care where it is above the x-axis. What I care about is that it's above and it's heading toward this very first 0 right here. So I do something like this. It does not have to be perfect, okay? Then what I notice is from about -1.5, so right from this bump to the next bump, my graph of f is decreasing, which means that my derivative has to be below the x-axis. So, I don't know why that keeps happening. What I'm going to do is I'm going to head this down below the x-axis, but it has to start heading up to the 0 that's to the right of it. And then I stop. It could be deeper than that or something. It doesn't matter, okay? And then what I notice is that the graph of f from about 2.5 to 4 begins to increase again, which means my derivative must be above the x-axis. So from that point, I'm just going to do that, and I'm done. The red graph is the graph of f prime. It's the derivative function. I know it's some kind of a quadratic. I don't know what its formula is, but that doesn't matter. I've sketched it. That's all that matters, is that you can sketch it. Otherwise, what I would have to literally do is sit there and draw a tangent line to every single point, which is impossible in itself. Technically, to every single point along this thing to find the rates of change at every single point. Or I could just choose a bunch of points, you know, and extend my tangents out, and that would still give me a good graph. But rather than that, we've got this here. So why should we do all that work? AP doesn't expect you to, nor does any professor of higher mathematics. So you're good just with a sketch, right? So he does ask you in this particular problem to estimate the derivative at certain values of x. So if I were to do that, you know, all I would do is draw a tangent line when x is -4. So I've got this pretty steep tangent line here. And when x is -2, it's less steep. When x is 0, it's pretty steep right here. When x is 2, and then when x is 4 again, so something like this. And you would estimate them. And I would say maybe this is about a, I don't know, a 4. You notice he's got 3.5. All right. So, you know, if I wanted to be precise, I know this is the point -4, -3, and I could extend this up to maybe it goes through this little grid right here and use those two to compute the tangent line. So sometimes you're going to have to do that for a couple of points, but rather than that, this is what they're looking for. Can you sketch the derivative graph given the graph of f, right? And here's the graphs superimposed. So as you can see, well, I erased mine, but his f prime graph is probably a lot nicer than mine was. But that's okay, because what the grader is going to grade you on is, number one, are the zeros in the right places? Yes, they are. There was a bump here. I projected it as a 0 on the x-axis. So I got the point for the correct zeros. Is my derivative graph above and below on the right intervals? Yes, it was. So that's how you're going to get graded on it, okay? The derivative of a function defined numerically, I said we're going to skip this part. So don't worry about this part yet. We're going to go back there later on. All right, and then what Best does is he gives you the formula, and I know this is hard to see, but this is f of x plus h minus f of x. So again, like I showed earlier, it's f prime of x is the limit as h approaches 0 of f of x plus h minus f of x all over h. The other one you had, the first one you learned, was the derivative at a point. This is at a point. The point x equals to a was the limit as h approaches 0 of f of a plus h minus f of a over h. So you notice the formulas are exactly the same, except where there's an a here, there's an x here. That's the only difference. This one's at a point, so you're going to get a number. This one's over the entire domain, so you're going to get a new function. And you can see that really nicely with this problem right here of x cubed. You know, you have to use the limit definition to find the derivative. And I'm highly disappointed in George because he took some shortcuts here and didn't write his limit, all right? But what I have to compute is the limit as h approaches 0 of f of x plus h minus f of x over h, okay? So when we figure out what x plus h cubed is, because remember this is x cubed, so I'm going to plug in x plus h everywhere. Let's do it, actually. Let's do this one. And then I think I'm going to have to take a little rest. Come on, take me to the page. All right, so if f of x equals x cubed, and we want to find the derivative of that function, then what we know is that this is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. Well, the hardest part to compute is this piece right here, because it's a cube. This part we already know. F of x is just x cubed, so I already know what's going in this part, but it's this part here. So what is f of x plus h? Well, it's x plus h, the quantity cubed. And what that is expanded is x cubed plus 3x squared h plus 3xh squared plus h cubed. Okay, I'm using a binomial expansion in Pascal's triangle. I've memorized this from, you know, a billion years of using it, so it's really easy for me to expand out. F of x is just f of x. So again, f of x is just x cubed. Now let's put it in the formula. Let's use light blue. So we've got that f prime of x is equal to the limit as h approaches 0 of x cubed plus 3x squared h plus 3xh squared plus h cubed minus, and I'm just using the minus that's in the formula, x cubed all over h. And nicely, the x cubes cancel. So that gives us the limit as h approaches 0 of 3x squared h plus 3xh squared plus h cubed all over h. And again, we've got to get rid of that h from the denominator, so we factor the numerator. So we've got the limit. You notice what I'm doing here, and I'm saying this because after grading a lot of homeworks, a lot of you are not writing stuff down, and I know you're not used to AP, but you have to write everything for the AP exam or you lose points, all right? So this limit notation needs to stream on down every single step until you take the limit, and then that's when it's going to disappear. So don't forget that. So if I factor out an h in the numerator, I'm left with 3x squared plus 3xh plus h squared all over h, and then I can get rid of those. And that gives me the limit of what's left. Well, can I simplify what's left? No, I cannot, okay? I can't factor it, I can't do anything with it. So when that happens, now it's time to take the limit. And the limit just means to take the 0 and plug it in for every term that contains an h. And then that limit notation is going to go away. So what it equals now is 3x squared plus 3x times 0 plus 0 cubed. And again, you wouldn't write this, okay? This is trivial, but we know that 3 times x times 0 times anything is 0, and 0 cubed is 0. So those go away. And so we get 3x squared. So what I would say is that f prime of x is 3x squared, and that is the true derivative. When you learn rules, you'll learn to take that very quickly without having to go through all this work. But for right now, you have to use the limit definition. Okay, so I didn't get a number. I got a new function, and the new function is a quadratic. The old function, or the original function, was a cubic, and it went down a power, and it's the derivative over the entire domain of x cubed. Okay, it's a new function, the derivative function. So let's go back to 2.3. Let's see, we were skipping that part. Here we were. So here it is here, okay? There's, he used the limit definition a little bit loosely. You're not allowed to do that. When you get into upper mathematics, then you can, but for AP, you are not allowed to. And you'll know because it's going to hit you hard on your grade in the class. If you don't, because I'm going to nail you every single time. You'll change it real quick when it comes to your grades. All right, the other thing we discussed in this section is notation. This is called Lagrange or prime. We say prime notation. We say this as, let me get my laser pointer, f prime of a, or the derivative of the function f at the point where x equals to a. Okay? It's called prime notation, but Lagrange invented it. The dy dx symbol means if you have a function y, let's just say, same function we had before, right? I could write that as f of x equals, so I could write this as f of x equals x cubed, or I could write it as y equals x cubed, right? Because y equals f of x, right? That's a cube. Oops, too big. Let's try again. F of x is equal to x cubed, y equals x cubed, okay? So if I want to find f prime of x, I'm using Lagrange notation or prime notation. We say, well, that's 2x squared, or sorry, 3x squared. If I'm using y, what I'm doing is I'm saying the derivative with respect to x of the function y is equal to the derivative with respect to x of x cubed. So I'm just adding this d dx, which means in words the derivative with respect to x. Now, you see here on the left, think of it as multiplying y over 1 to d dx. You get dy dx. So what I'm saying here is the derivative of the function y with respect to the variable x, okay? And when I take the derivative of the right-hand side, okay, through whatever process I'm using, I'm going to get 3x squared, okay? So that's Leibniz notation. So both of these notations we're going to use a lot. You're going to start seeing this one a lot more very shortly. And here's another, example with the function x squared. Again, I could write this as y equals x squared. So on the left side, I say the derivative of the function y with respect to x is equal to 2x. And this one we don't ever use. All right, so that's just notation. And here's a problem where they want you to verify that the derivative of a function is negative 1 over x squared if y equals to 1 over x. And so they used, or he used, again, in a terrible way, he used the limit definition. But let's just do this. Again, let's just do one more for practice. If we have that y is equal to 1 over x, and I want to find the derivative of y with respect to x, well, that's the limit as h approaches 0 of f of x plus h minus f of x all over h. Now, these get a little bit ugly, and this is where being really good at algebra and fractions is going to help you. Because when we have to evaluate f of x plus h, well, that's 1 over x plus h. f of x, of course, is itself. It's 1 over x. So when I put this back together, I've got 1 over x plus h minus 1 over x all over h. I have complex fractions. I forgot my limit. Okay? And now what I'm going to have to do is get on top here a common denominator, right? And that's easy enough. It's x minus x plus h quantity over x times x plus h all over h. What? You better brush up on those algebra skills. The limit as h approaches 0. So look, all I do to get a real quick common denominator is I cross multiply, and then my common denominator will be this denominator times that denominator. Okay, now this is all in a numerator. So you notice this is all in a numerator over h. However, this numerator can drop into that denominator, or sorry, this denominator in the numerator can drop down to this denominator. So what we can write this as is x minus quantity x plus h all over x times x plus h times h. And if I simplify the numerator, then what I'm going to have is x minus h over x times x plus h times h. Don't ever, when you're dealing with the limit definition, don't ever start distributing and combining stuff in a denominator, okay? Because you're going to make a lot more work for yourself and you're probably going to make some errors. So just leave it alone because things are going to cancel. These two cancel, and so we have the limit as h approaches 0 of negative h over x times x plus h times h, and those h's are going to cancel. So we're finally left with the limit of negative 1 over x times x plus h. Now I can't simplify that anymore, so at this point I'm going to actually take the limit. When I do that, that means I'm going to plug a 0 in for every h that I see. So this becomes negative 1 over x times x plus 0, or negative 1 over x squared. And that's it. Okay, and that is the correct derivative. If you knew the quotient rule, you could do that much simpler, although most students hate the quotient rule. You can also use a power rule on this too. So once you learn the rules, again, you can find the derivatives of a function. But again, I'm getting a new function. So f prime of x here, or y prime, whatever you want to call it, is equal to negative 1 over x squared. So I get a brand new function. All right, back to the pages. And that's it, okay? And then what you had to do was some curve sketching. You had to fill in some tables, filling the missing entries in the tables. I did see several emails for questions on 2.3. Just quite not up to it. I've been sleeping like all day practically, except when I went and got my test today, this afternoon. And I'm exhausted right now. I'm just not feeling well. So I think I'm going to call it quits here. Somebody asked me to post the Zoom video from 2.3, and again, I can't find it. That's why I made this one. So I hope this helps. And again, if you have questions, please email me and let me know. I'm going to try and get to some of your specific questions on this section tomorrow. And I hope to see you on a live Zoom session on Friday. Okay, so I hope this helps. Have a great night. See you soon. Bye.